Good afternoon. You've seen the professor already. Now, I bet you already heard his name many times in many classes. You've read his name in many books. Now you're seeing him live, Mr. Peter Atkins, presenting some curious aspects of thermodynamics. Please welcome once again.
Well, thank you very much for inviting me here. It's always a great pleasure to come to this country, been many times, but this is the first time I've come to this university. And I think it's a wonderful institution that you have in the sense of this meeting. I would also like to thank my hosts for their very kind and considerable hospitality. I think it's simply a sign that we're starting half an hour late, that we've been enjoying hospitality throughout the morning and throughout lunch. I'm going to talk about, can we have the lights down, please, the lights down. This is not where I normally work, but I wish that it was the place that I work. But this island is going to appear as an analogy throughout my talk. I'm going to use it in a variety of ways. And the first way that I'm going to use it is to show you that science, and indeed thermodynamics, as a part of science, is not just an island, but it's part of a continent. So you should never think of the science that you are studying as being isolated from other regions of science. So what I'm going to try to do is to show you that when we're thinking of various aspects of thermodynamics, then it actually illuminates many other regions of science. And I'm going to argue that thermodynamics tells us something about quantum theory. I'm going to argue that thermodynamics shows us even something about cosmology. And it helps us answer some of the very deepest questions that you encounter in science. And I'll explain what I mean as I go through. What I've tried to do is to identify aspects of thermodynamics and quantum theory that you all know already, but maybe have not really thought about. And so I'm going to try to encourage you to think deeply about what it is that you already know. So first of all, let me talk about connections, and in particular, I'll talk about links between thermodynamics and quantum theory. There is a very deep link, an extraordinary link, which you might not have explored yourself, which is that time and temperature are very closely related. Not simply because they are both represented by the letter T, of course. If you go back to the Schrödinger equation, then there's the Schrödinger equation. And I will express it in terms of the density rather than the wave function. And the equation then becomes that. And because I want to deepen your understanding, let me change the notation a little bit to this, so that I now write this equation effectively as that. That is the basis of quantum theory. Almost everything that you do in quantum theory comes from analysing the consequences of this equation. If you turn to thermodynamics, and if you turn specifically to statistical thermodynamics, then the deep equation is in terms of not the wave function, but the partition function. And the energy is given by this expression. And you can see that effectively the basis of thermodynamics is really almost identical to the basis of quantum mechanics. And you can go directly from here to here if, instead of dealing with the temperature and the time, you replace time by complex imaginary temperature. So the first message that I want to get across to you is that temperature is imaginary time, or if you prefer, time is imaginary temperature. It's amazing that you can go from the equations of quantum mechanics to the equations of thermodynamics simply by going from a real value, the temperature, to an imaginary value of the temperature, which we call time. So you can think of temperature and time as being effectively the real and the imaginary parts of a single quantity. That's very important, because it means that if you can do calculations involving time, like time-dependent perturbation theory, then you can switch to important equations in thermodynamics simply by replacing real values by complex values. But there's a deeper thought there, because if you think about where that statistical equation, the statistical thermodynamics equation, came from, it came from thinking about replications of the real system, all at the same temperature. And in thermodynamics, what you do, you take an average over the behavior of many systems, all at the same temperature. So what you see in practice, what you see in a test tube, is simply an average value of many systems which all have a common temperature. Perhaps it's the case, and this is the thought that I want to leave with you, and I do not really understand the answer myself, but I'm just trying to make you think. Maybe that when we think about quantum mechanics, and what we're really doing is thinking about many replications of the system we're talking about, all at the same temperature, all at the same time. And we just observe the average over all these systems. So maybe what you're looking at now, you're looking at me in the real world, maybe I'm just an average over many replications of me in some sense. Because that's how, first of all, you can generate thermodynamics, and that is how, in this case, you can generate quantum mechanics. And there's a question: if temperature can be thought of as imaginary time, or time can be thought of as imaginary temperature, are there other quantities that you might also encounter imaginary aspects of? What would imaginary volume be? Imaginary time, imaginary temperature is time. What would you think of imaginary volume? Do you ever encounter imaginary volume? Well, there's one place you do, but you probably don't realize it. And I have no idea what it means. So I'm going to show you where you encounter it and leave you to think about what the possible physical significance is. All of you know about the van der Waals equation. There it is. Suppose I were to rearrange it to get it as a function, as V as a function of the pressure. Then what I get, of course, is a cubic equation. What are the roots of a cubic equation? Now, I'm going to show you now the worst slide that you will ever see in your lives. And this, I'm going to show you something that you should never exhibit in public. Because I promise you, it is a slide that should never, ever be shown. I'm going to show you what the roots of this cubic equation look like? If you use something like Mathematica, then what you get is something like that. But notice, forget all the symbols and so on, and notice that you get the square root of -1 going. So there. So these are complex. So it means that the volume as a function of pressure and temperature can be complex, have real and imaginary components. I have no idea what that means, but here I'm just planting that in your mind as a thought. If I plot, I'll go to this one, if I plot those roots, then you can see that the isotherm comes out, but there's fragments of all possible roots. So there's something very deep going on, and I simply do not know what physically imaginary volume means. Think about it. That's really a challenge to you today. Everyone knows about adiabatic change in thermodynamics. It's when you take something like that in a sealed, thermally isolated system, and you compress it, and the temperature goes up. So there is an adiabatic compression of a gas. Doesn't matter what gas. You know that the temperature goes up when you compress the system. But there's also the word adiabaticity. Adiabatic change is used in quantum theory. And is there a connection between adiabatic change in quantum theory and adiabatic change in thermodynamics? What I mean by adiabatic change in quantum theory is something as follows. Suppose you apply a perturbation, and here's the perturbation, and you apply the perturbation suddenly, then the system jumps around. It's like when you hit a bell. It's a non-adiabatic change because you're forcing it into oscillation. If I apply the perturbation more slowly, then you can see that the system jumps around less. If you apply the perturbation very slowly indeed, then the system responds very smoothly. It doesn't jump around between states. States gradually change as you change the system very slowly. In the connection between thermodynamics and quantum theory, why the term adiabatic can be used for both types of change, I can represent like this. Here I've got energy levels populated with a Boltzmann distribution. So there's the quantum mechanical part of what I want to talk about. And here is my piston that I'm going to compress the system. And if I compress it very slowly, so the thing comes in slowly, we'll go back to, what you see is that the populations remain effectively a Boltzmann distribution, but they're reaching up to higher values. So the system is actually getting hotter. So if you think about what happens to a particle in a box, as you gradually, slowly squeeze the box, then you see the connection between the thermodynamic aspect of adiabatic change and the quantum mechanical aspect of adiabatic change. What about cosmology? I claimed that thermodynamics illuminated cosmology. A really big question. One of the big questions that confronts scientists, philosophers, and rather uselessly theologians is that where did all the energy come from at the creation of the universe? I mean, some really massive event must have taken place about 14 billion years ago, and all the energy must have come from somewhere. What can science say about that? Well, it begins by saying, what is the total energy of the universe? Because let us measure something. And so when you look at the universe, and there's obviously a small fragment of it, you immediately feel that there is an enormous energy in the universe. How could all that energy come into being? Well, what a scientist does is to measure the energy, the total energy of the universe. And the scientists would do it as follows. They would weigh a galaxy. Okay? And so, having weighed the galaxy and determined its mass, you take its mass, you multiply it by c squared, and you get the energy represented by one galaxy. Then, of course, you look at the whole universe, and you say, I'll weigh that galaxy. And what I will get is some energy. I will then weigh this galaxy and add it to that energy. And you can see if I do it for this galaxy, then I get that. This galaxy, I get that. And in the end, when I've done it for every possible galaxy in the universe, I'll have some super colossal value of the energy. I don't know what the actual number is for the energy, but I know that I can, in principle, determine it, and it's going to be colossal. That's a real problem for some people with cosmology. Where did it come from? Well, scientists, and this is something that all of you are learning, is circumspect, and they look around and say, have we considered all the contributions to the energy? And there's one contribution that this calculation ignores, and that is the interaction gravitationally between the galaxies. When two galaxies attract each other, of course, the energy is reduced. So if I allow for the gravitational attraction between this pair of galaxies, then the energy that we calculated originally goes down. So let's do it, so it's gone from this value down to that value. Now let's take into account that gravitational interaction with that gravitational interaction. Down it goes again. This one with that one, down it goes again. You can see where this might be leading. It's a speculation, but it's a speculation that is becoming more and more plausible, especially when you take into account dark matter, that if you include all the interactions between all the galaxies in the universe, then the energy goes all the way down to zero. In other words, there is no energy in the universe. Now you can see how that simplifies the problem of what went on at the creation. The energy didn't have to come from anywhere. Because there isn't any, it didn't have to be created. What science does, as it progressively moves towards understanding the deepest questions about the nature of the universe, like what happened at the creation, it simplifies what needs to be answered. And here is really a major simplification. So before the existence of the universe, when there's absolutely nothing, not just empty space-time, but absolutely nothing, the energy was zero. And it seems to be the case that now there is still nothing. So when the universe was created, much less had to happen than you might have thought. So the ultimate study of thermodynamics, and I hope that I'm going to offend any thermodynamicists present, is the study of nothing. But it's actually a much more interesting form of nothing than what nothing used to be. Not many women have contributed to thermodynamics. One who has, but didn't realise it, was the German mathematician ENEQUI, who came up with an extraordinary theorem, which I'm going to tell you in a moment. And I think it's of profound importance because it helps we scientists to answer another very deep question which has puzzled philosophers and worried theologians. Theologians should be worried, in my view, but philosophers are worth thinking about. Which is, where do the laws of nature come from? I mean, we're surrounded by what looks like matter behaving in uniform ways, and we rationalize all those ways through applying the laws of nature. Where did the laws of nature come from? Were they imposed by some kind of supreme court? Or is there a simpler explanation? Well, scientists always go for simpler explanations. And let me speculate on one law of nature to show you how you might understand it. And it is probably the most important of all the laws of nature. What Noether's theorem says is that wherever you have a conservation law, such as energy is conserved, then there is the reason for that law can be found in an underlying symmetry. So Noether's theorem finds connections between symmetry and conservation. In our case, the conservation of energy comes from a very special symmetry. It comes from the uniformity of time. So if time goes tick, 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 uniformly on a cosmic scale, then Noether's theorem predicts that energy is conserved. If energy, it was not uniform, so that it went tick, 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 like it does in some lectures, then energy would not be conserved. So you can understand the first law of thermodynamics, effectively the conservation of energy, by trying to understand why time is uniform. So why is time uniform? I've already argued that, let me come back to those in a minute. Here's the universe before it was created. Okay? Absolutely nothing. If you've got absolutely nothing, it must be uniform. Okay? Because it's not uniform, it means that you've got something. And here we've got, as you see, absolutely nothing. I've already argued that not very much happened at the creation, because energy was not created. It just sort of turned into a different kind of nothing. So suppose nothing happened to nothing. That means that the uniformity that there was before the creation was preserved when space-time came into existence. And once you've got uniform time, you've got the conservation of energy. And once you've got the conservation of energy, you've got, on the one hand, you have got the first law of thermodynamics, but on much more important level, you have got the whole nature of causality, the fact that you can understand and make predictions about the workings of the physical world. So you can begin to see that if you accept the view that nothing happened at the creation, I know it doesn't sound very plausible, but suppose you accept the view that really nothing happened then at all, not only is the universe easier to, the coming into being of the universe, a much easier problem than you thought, but also you can see that one of the most important laws of nature can be explained too. But are there other, that is, if time is uniform, then energy is conserved. Are there other fundamental laws of nature that can be argued about in the same way? Well, there is one. Suppose this represents not time, but space. Suppose for the same reason, because nothing happened at the creation, when space was formed, it too turned out to be uniform. Then the consequence of Emineta's theorem is that linear momentum is conserved. So when momentum before a collision and after a collision is the same, really it's the basis of Newtonian mechanics, then you can now begin to see why that law exists. And of course, once you've understood that, you understand the whole of the foundations of classical mechanics. And let me go back. Another law related to symmetry, the conservation of angular momentum. We know that angular momentum is conserved. Why is angular momentum conserved? Well, according to Emineta's theorem, it is because space is isotropic. If you go around a point, space does not change. Space-time does not change. So you can begin to see that yet another fundamental law of nature emerges from understanding the symmetry of nature. So when you go back to people like Kelvin and Joule, who thought that they were looking at the conversion, the equivalence of heat and work, what they were really doing, and what you do whenever you do a calorimetry experiment, is really not studying simple mechanical systems like this. You were really studying the shape of space-time and seeing that it was uniform. There are other laws that I will skip through this little bit. You can also show that the preservation of uniformity, it also leads you, and I won't go through this argument in detail, I will just mention it, leads to an understanding of the presence of the electromagnetic field. By looking at the uniformity, the fact that the Schrödinger equation gives you wave functions which effectively remain the same as you change the phase of them. So I won't go into that into detail unless you ask me later on. But bear it in mind that electromagnetism also, in my view, emerges from absolutely nothing happening at the inception of the universe. I'll skip all those, I don't really have time. But a consequence, okay, let me go back one stage. I've got the Coulomb potential. Everyone knows that the Coulomb potential here is crucial to understanding the structure of atoms. So now I'm going to make a transition from talking about thermodynamics, from talking about aspects of quantum theory, in particular the consequences of the Coulomb potential. If I were God, and I wanted to give mankind a universe, then first of all I wouldn't trust mankind with any energy, and you can see that indeed he didn't trust us with any, but I would also give him or her the most beautiful potential in the world. The chemical potential, the Coulomb potential is extraordinarily beautiful. It's beautiful because it's obviously spherically symmetrical. Doesn't matter, there's no direction implied in this formula, just distance from a charge. But when you examine the Coulomb potential deeply, you find that it is also symmetrical in higher dimensions. It's still fully symmetrical in 4 dimensions, 5 dimensions, 6 dimensions. And so in that sense, it is the most beautiful potential that you can possibly have. One consequence of its beauty is something that often puzzles people, which is the degeneracy of a hydrogen atom. We all know that 2s, a 2p, 2pz, a 2px orbital, 2py, and so on, have exactly the same energy in a hydrogen atom. So the hydrogen atom has a lot of degeneracy. It's always the case, and I will emphasize always, that degeneracy arises from symmetry, and in particular, the ability to transform by a symmetry operation one state into another. That's very easy to see for these p orbitals, because you simply rotate it from the z direction to the x direction. The Coulomb potential is symmetrical in 3 dimensions. So it's easy to see that these two must have the same energy. But what about this one? How is it possible to rotate this 2pz orbital into that 2s orbital? How can you rotate that sphere into this pair of spheres? And this is where the fact that the Coulomb potential is symmetrical in higher dimensions becomes important. Let me talk about 2 dimensions and 3 dimensions rather than 3 going to 4, and that will show you what I mean. Here's one p orbital in 2 dimensions, just symbolized by the difference in sign and the node across here. Here's the, say, px orbital, and here's the 2s orbital in 2 dimensions. And it's obvious that you can go from here to here simply by rotating through 90 degrees. But how do you go from here to here by rotating? Well, you step out of 2 dimensions and you think in 3 dimensions. And in 3 dimensions, you could think of a sphere resting on a plane. And just so the plane is just the projection of each half of the sphere. And obviously, I can go from this p orbital to that p orbital simply by rotating the sphere around the vertical axis. But I can also rotate that sphere around, say, this axis. And what I then get, of course, when I project out the wave functions, is the equivalent of the 2s orbital. So by stepping out of 2 dimensions into 3, and using the symmetry of the Coulomb potential, you can account for the degeneracy in 2 dimensions. and by analogy in higher dimensions. And you can do that. It's quite a good exercise to see what shape you need in order to rotate this orbital, whichever it is, a G orbital, into this rather complicated orbital here. And the shape you need is something like that, because the projection gives you this two-dimensional image, rotated through a horizontal axis across here, and what you get is that other shape when you project it out. So you can begin to understand, or you can begin at least to see, that the origin of the degeneracy of the hydrogen atom, enormously important really, the origin of that degeneracy, which is puzzling when you just look at it in ordinary 3 dimensions, actually is a consequence of the higher dimensional beauty of the Coulomb potential. There's some more. Okay, let me go a little bit further. Let me deepen understanding. A great hero of mine, Ludwig Boltzmann. It's almost good to look inside people's heads to see what they're thinking. And so let's think about Boltzmann for a while. Where does the Boltzmann distribution come from? It's really a deeply important aspect of nature, and I shall argue a little bit more about it later on. But of course it comes from randomness. If I were to take a set of energy levels and just populate them with molecules, then I could get various distributions. I could get that distribution, but it's of very low probability. I could get this distribution. Still a higher probability, but nevertheless still a very low probability. The highest probability is one that looks like that. That is the most probable distribution. So if you lie on the floor and you throw books at a bookshelf, this is the distribution that you will most probably get. And of course, that fits an exponential. And the exponential is the shape of the exponential is determined by a single parameter, which we call the temperature. So I think when you want to talk about the nature of temperature, what you should do is to realize that it is the single universal constant that, regardless of the nature of the energy levels, tells you the distribution of molecules over them. That's all the temperature is. And I think it's through Boltzmann's short-sightedness, physically, but actual long-sightedness, scientifically, that we now understand more about the nature of temperature. And of course, if this T changes to a lower value, then the distribution looks like this. Lower temperatures, we understand we get this distribution. And if we change the temperature to this parameter to a higher value, then we get a distribution that goes up there. So here's the desert island again. If I wanted a companion on my desert island, intellectually, I would ask for Boltzmann. I think that the Boltzmann distribution really is absolutely fundamental to understanding everything there is about chemistry in general. Because the fact that most of the molecules are in lower states means that you are able to discuss structure, which persists for long times. But the fact that there are molecules in very high energy states means that you are also able to discuss chemical reactions, because those states can change. So really, the Boltzmann distribution, I think, is the most important and elucidating expression in the whole of physical chemistry. Go back to this island again. When I taught in Oxford, what we do, we teach by tutorials, very tiny groups of perhaps one person, two people. Very first tutorial, I think, I'm not quite sure what the reason was, I like to frighten my students to the core, just to shake, if you like, their confidence, but also to encourage them to think more deeply about what we were talking about. If you were marooned on a, suppose you knew nothing about thermodynamics. That might be true, of course. But suppose you know nothing about thermodynamics and you were shipwrecked and you found yourself on a desert island with only the vegetation, effectively, and maybe the water as your tools, as your equipment. Could you derive the laws of thermodynamics? So I would allow you to measure work by seeing how high you could raise a coconut. Okay? I could certainly measure length with all the rings on the palm tree. I could measure volumes, because I could open a coconut and use this as a measuring tool. I could create, using vines, a pendulum, so I could measure time. So with those instruments, could I derive thermodynamics? What I'm really talking about there, it's not really a desert island. It's a component of classical physics. This is the island of dynamics, where I'm able to talk in terms of work, I'm able to talk in terms of mass, of length, and of time. So it's really whether you can consider classical mechanics using just the concepts of mass, length, and time in order to derive the laws of thermodynamics. I'm going to leave that question with you and see whether you can answer it. Here's another desert island. Well, here's another desert island that should not be a desert island. Science is such a wonderful human cultural activity that it should not be insulated by an ocean from the general public. It's very important, I think, for all you who understand science to go out and share with the public the insight and understanding that it gives. One thing to show, I think, is the power of abstraction. I think that thermodynamics arose from studies of the steam engine. But people like Kelvin and Clausius and Carnot thought about the steam engine in an abstract way. So they thought in terms of hot and cold reservoirs and the flow of energy, the creation of work, the use of the motion of energy as heat. If you think abstractly, then you don't need all the physical attributes of a steam engine. You might also find that you can apply the same reasoning to things which don't look very much like steam engines, like bodies and metabolism and so on. So, very important aspect of science, in my view, is the recognition of behavior from concrete observation but the conversion of it to an abstract statement, and then the discovery that once you have abstracted, you can apply extremely widely. Very important aspect of the procedure of science. I would also, talking about thermodynamics again to the general public, try to explain the difference at an atomic level between work and heat. Because understanding at an atomic level actually helps elucidate, just as we saw with the elucidation of temperature. And I think if you are talking about the thermodynamics, then you would say, well, what I understand by work at an atomic level is the achievement of the uniform motion of atoms in the surroundings. So here work is being done, and a weight is being raised, and all the atoms of the weight are moving in the same direction. Work is always associated with the uniform motion of atoms. Whereas heat, if I simply want to transfer energy as heat, then what I use is the chaotic motion of atoms in the surroundings. They don't move in bulk. They move locally, but randomly. So heat makes use of disorganized motion in the surroundings, whereas work involves uniform motion in the surroundings. And then there's that second most wonderful law of nature, the second law. It distresses me greatly to think that there are many corpses in cemeteries throughout the world of people who did not understand the second law of thermodynamics. I think that those corpses must be utterly miserable, going for an eternity without knowing the second law. Second law, in my view, is the most illuminating of all the physical laws of science. So I think it's very important that you try to convey it to the general public. And it's very easy to do, simply by saying that this doesn't happen. That doesn't happen. This does happen. So matter and energy tend to disperse in disorder. In other words, things get worse. And most people can understand that things get worse. What they really don't understand is that that's the second law of thermodynamics that they're observing. And I like to show that even though things get worse globally, then locally structures can emerge. Here, for example, is a symbol of something getting worse. This might be the combustion. Well, here's something. Suppose there is a mechanism by which you can tap into this process of dispersion. Then you might be able to use it to build a structure. So even though the world overall is getting more disordered, locally structures might emerge. This might be a hydrocarbon fuel in an engine. This is its combustion. So the carbon dioxide and the water molecules disperse in disorder, and the heat, the energy that is released as heat, disperses in disorder. This might be a physical engine. This might be a pile of bricks, and this might be a cathedral. So the dispersion here drives the emergence of structure here. This might be breakfast. This might be digestion. This might be the metabolism of the products of digestion. These might be amino acids, which are being, so as you eat, so you build structures on a molecular scale, in this case, proteins. So what we're beginning to see, what the second law illuminates, is the connection between that great energy disperser in the sky, the sun, its driving of the emergence of the biosphere on Earth, and our consumption of the biosphere to lead to the construction of organs. And the second law illuminates all that kind of thing. How much longer have I got? How much longer? Wake up. $15. One time. Okay, I've got 15 minutes. One of the things that happens, of course, is the way that scientists take qualitative ideas and render them. I'm going to skip clouds. You all know about clouds. And let me go on. Let me go on to back to a little bit of more quantum theory. I use my 15 minutes for talking about the hydrogen atom. We all know that the consequence of talking about the structures of atoms, in particular using the hydrogen atom as the basis of what we're talking about, leads to an understanding of the periodic table and the periodicity of the properties of the elements. What I want to do is to explore hydrogen atoms in dimensions other than 3. What would the periodic table look like if we lived in a one-dimensional world? Well, you can do that. There's the universe in a one-dimensional world, just a single line. And I'm going to talk about the hydrogen atom that would exist in that universe and conclude from it the shape of the periodic table. There's the potential energy, and it's very easy to solve the Schrödinger equation for the states of the one-dimensional hydrogen atom. They all depend upon 1 upon n squared, just like three-dimensional hydrogen atoms. And there they are, some of them, and there's lots of states up there. And if you now think of how to populate these states with electrons using the Pauli principle, it's like you do with the usual real hydrogen atoms, then, well, those are the wave functions, then this would be the periodic table that you would get. There would only be 2 groups, and this would be one group, and this would be the other group. 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on. Quite easy to build that. But suppose you lived in 2 dimensions, and that you wanted to know what the periodic table would look like if atoms were just 2-dimensional beings, like this. There's the potential energy again. The solutions can be found analytically and exactly, and they depend upon n plus a half, but it's still more or less n squared, rather like in 1 dimension. And here are the wave functions. I'll show you that in. Here are the wave functions for the hydrogen atom. And those are the probability densities for the hydrogen atom in 2 dimensions. If you mess around with the energy levels a bit, what you can now predict is what the periodic table would look like in 2 dimensions. There would be this number, well, there'd be infinite number of groups. This would be the first group 1, hydrogen, lithium, boron, magnesium. Not very familiar, but nevertheless, this is what you would get. Suppose you were thinking about hydrogen atoms that were inside out. What do I mean by hydrogen atoms that are inside out? I mean, when instead of the electron being trapped to a nucleus, it's actually confined by a wall. So I remove the nucleus and talk about hydrogen atoms that are just cavities. Sort of thing that really does occur in real matter. But this time, just thinking about 2 dimensions. And these are the shapes of the wave functions that you will get. Those are the probability densities in 2 dimensions. And this would be the beginning of the periodic table: hydrogen, helium, lithium, beryllium, and so on. So you can begin to see that you can construct the chemistry of chemists in universes with other than 3 dimensions. I suppose that we'd extend it to 3-dimensional atoms. 3-dimensional atoms without a nucleus. So in other words, an electron or electrons inside a spherical cavity, like this. There's the electron distribution inside this cavity. Then once again, you can work out the energy levels, and these are a representation, which I actually adapted, of the wave functions. And now the periodic table really does get very complicated. But it's not unrealistic in the sense that electrons trapped in cavities do, to some extent, behave like inside-out atoms. Another question. At the moment, we know about 120 elements. And we know that the periodic table has an S block, a P block, a D block, and an F block. Suppose we knew thousands of elements. What would the periodic table look like? 3-dimensional real world this time. What does the continuation of this pattern look like? And you can guess what it would be. It would be something like that. Let me turn it around a bit. So there is the periodic table, what it will be when we know 2,710 elements. At the moment, of course, we're up here. There's element number 100. We know a few more than that. This is where we will be when we know element 1,000. And so this is really eternity going on. But this is just an amusement in thinking about what the table would look like if you were to go to very high atomic numbers. Well, I'll conclude at this point. What I've tried to show you is that no aspect of science is an island. It's not an island in the sense that a study in one region can illuminate aspects of another region. It's not an island that is an isolated cultural activity, because we are part of human culture and we must spread our knowledge away from our little islands of activity into the general public. Also, it's not an island. I don't know how I'm going to say this, so I'm not going to say it after all, because I prefer to know what I'm saying when I'm saying it. So I hope to show you, that I've shown you, is that this island of our activity illuminates an enormous range of human activity. And at that point, I will thank you for your attention and come to a conclusion. Thank you.
Questions? Any questions for the professor? Any ideas about imaginary volume? Any doubts?
Good afternoon. I would like to know what you think about why quantum mechanics behave like they behave. We know a lot of phenomena, we know how to explain it with math, but why?
I think that there are two origins of the laws of nature. One I explained, the uniformity and symmetry. But there's another one, and I think that is anarchy. That is the absence of laws leads you to the existence of laws. And what I mean by that is, suppose you were to think of the propagation of light. A law of matter is that light travels in straight lines, simply speaking. Why does it travel in straight lines? Now, suppose you say, well, I know that light is a wave motion, and I allow it to do that as the path. This path ends up with a certain phase. It has a neighbour, which ends up with a slightly different phase. It has other neighbours, and so all those different phases are different. And so the light that comes by that group of paths washes itself out. But this straight line path has neighbours which almost have the same phase as the straight line path, and they do not annihilate. So if you say, light, travel wherever you want, do whatever you want, I don't care, go anywhere between here and here. Only this path turns out to survive. So if you allow complete freedom of action, that is anarchy, you get a law of nature. And there's a very close relationship between the propagation of light, and because matter is also wave-like, you also get quantum mechanics and wave mechanics out of it by the same argument. So the Schrödinger equation really is an aspect of anarchy. And you might like to think that that is a general rule anyway. If you have a society that allows everything to happen, then it will annihilate itself, and only seriously effective societies will emerge. So I think anarchy is the root of lawfulness. So if you say that symmetry thing, nothing happening at the creation, is indolence, laziness, then I think there are two origins of the laws of nature. One is laziness, and the other is anarchy.
Thank you.
Any more questions? In the middle, yes?
Hello. I once read about a physician that was studying the question about time in quantum physics, and one of his conclusions was about that time simply did not exist. So you were talking about time and temperature being like close, nearly the same. If the conclusion in quantum physics is that time could not exist, aren't we actually erasing temperature from quantum physics?
So I didn't quite catch the question. You mean if time did not exist?
Yeah, one of scientists talk about that idea, the conclusion, since
Well,
Galileo and...
I think time has to exist. In the sense that if time didn't exist, nothing would happen. And so I think there is lurking behind your question, if I can slightly distort it into a slightly different question. I think there are reasons for knowing why time is only one-dimensional, not two-dimensional or three-dimensional and so on. Because I think that time effectively distinguishes different kinds of matter. And I won't go into that now. It's called matter and antimatter. Let me call it that. And if you could turn round in time, there would be no distinction between matter and antimatter. They would collapse. Because they're one-dimensional, you can't turn round in one dimension. I mean, I can turn round in 2 dimensions, but I can't turn round in 1 dimension. So once the time has come into existence as 1 dimension, matter and antimatter are distinguished. If time had come into existence as 2-dimension or higher, then matter and antimatter would not be distinct, and the universe would not exist. So the universe must have only 1 dimension of time.
But this Einstein talks about the fact that we can actually distort the time, since if we're traveling to the light velocity, we can actually distort the notion of time. We can
Yeah, I'm
shrink
sorry, I
time.
don't quite understand what you're saying, but I think I think the whole of science depends upon the evolution of time. The whole of daily life, the whole of national life depends upon the evolution of time. If everything happened at once, which sometimes it seems to, then I think there would be no hope of us emerging. So we emerge because there's time.
Thank you.
Yeah. So this might sound a bit silly, but
It won't be any sillier than my answer.
fair enough. So you said that before the creation of the universe, the energy was 0, and now
Everything is zero.
everything, obviously, yeah. And now it's still 0.
Yeah.
And according to that theory that says it happened the Big Bang, and then the expansion, then the contraction, expansion, and so on, in the moment of contraction, the energy would also be 0, right?
No.
No.
I think by saying that the energy is 0, what I'm actually saying is that the universe is flat. That is, it will expand, but asymptotically slow down until, it will always expand, but ever more slowly. It won't contract. If the energy was less than 0, it would contract. If the energy is greater than 0, sorry, the other way around. If the energy is greater than 0, it will expand forever. So I think to say that there is 0 energy means that the universe is cosmically flat and will expand but slow down. Now, obviously, dark energy plays a role there, the acceleration of the universe, and I don't understand the role of that, frankly. No one does yet. But we can be confident that the universe will not contract again.
Thank you.
When I say we can be confident, I mean it is unlikely, because it may be that on a very long time scale, the laws of nature change, that our current 4 dimensions of space-time might unravel into 11 different dimensions, and the laws of physics then would simply not known.
Peter, we know that the second...
Where are you?
I'm here.
Oh, sorry, yeah. You're dangerous.
We know that the second law tends to make the system to disperse, as you told us, even if locally they can be organized at the expenses of something that happens in other place. But my question is, how can you How can we, even knowing that, conciliate the spontaneous appearance of very complex organisms, like, for instance, living organisms?
Like you and me.
Exactly. How can we conciliate?
Well, evolution and natural selection are extraordinary manifestations of the second law of thermodynamics. I mean, that illustration I had about one mechanism driving another mechanism is all you need to understand. So that provided you've got a mechanism for coupling dispersion to construction, then anything, and you have plenty of time, then anything can emerge. And natural selection is such an extraordinary, powerful mechanism for, so once you've got life, once life has come into existence and has started to be able to replicate itself in an approximate way and fight for survival and fight for the opportunity to reproduce, then anything can emerge, as it has. You have emerged, I have emerged, and everyone else here has emerged. So there isn't any problem with the second law. The second law is all about increase in entropy globally, universally, and locally there are structures can emerge, provided that overall there is an increase in disorder.
So shall we have to speak also about an evolutionary theory?
Sorry, I can't hear.
Shall we also have to speak about an evolutionary theory for inanimate matter? I mean, I'm not concerned with the evolution of the living organisms.
Say it as a human, I didn't hear it through the microphone.
Okay, so shall we also have to consider some kind of evolutionary theory for inanimate matter?
Oh no, that's nonsense.
So how do you conciliate this spontaneous trend to generate the first living organism? I can understand the biological evolution.
Yeah, that was sheer luck. I mean, it was sheer luck that the first living organism emerged, whatever that was. And once, well, I think you needed two to be in competition. And once you got any competition at all for replication and the use of resources, it is inevitable that you get an elephant.
Okay.
Or something resembling an elephant. Yeah.
Any more questions?
No.
Can I make one? No. Well, I'll just speak from here. In terms of information theory, how does the microscopic relation between heat and work relates to information theory? Can I say that work carries information whilst heat is loss of information?
Yes, I would say exactly that. Yeah, yeah. So the work is the achievement of order, or the process of achieving order, and that's what happens in information theory. Yeah. Yeah.
With that conclusion, I think we're done for now. Applaud, please, one more time.
very much. That's really, I should be applauding you for being such a great audience. Thank you very much indeed.